Okay, I've got a problem up here on the board. This is actually very similar to question number 77 in your homework. And I think that's probably the toughest homework question in this section. So I wanted to make sure that we looked at something that was similar to that together. Okay. So we've got an object that is moving at 500 kilometers per hour. And I want to know what constant deceleration, so it's going to be slowing down, what constant deceleration will allow it to come to a full stop in 200 meters. Okay. So, first thing I'm going to observe is that these units don't match. I'm measuring velocity here in kilometers per hour, but I'm measuring distance in meters. So I got to pick one. I've got to be consistent. Either I'm going to be doing velocity in meters per hour, or I'm going to be doing distance in kilometers. I think I'm going to choose to do distance in kilometers. So remember, a kilometer is just 1,000 meters. So this is 200 thousandths, or 0.2 kilometers, right? 200 thousandths would be 2/10 of a kilometer, okay? So I can convert that right there, okay? But the thing that's tricky here is that I'm thinking in terms of velocity and position and acceleration. These are all functions of time. I'm told that the acceleration will be constant. I want to know what's going to allow me to come to a full stop in a certain distance. So position is going to be a function of time, but I'm not given the time at which I want to stop. I'm given the position at which I want to have stopped. So here's what I'm going to do. I'm going to write down that acceleration is constant, and it's a deceleration. I'm going to write it as negative d. That just means that the d that I'm going to be solving for is going to be a positive number. If I didn't put the negative sign there, d that I'd be solving for would just be a negative number. Okay. But then I'm going to have time, and I'm going to have position, which is a function of time, and I'm going to have velocity, which is a function of time. And these are things that are changing. The acceleration is constant. So I can sort of declare time 0 is when this problem is starting. Okay. So at time 0, I know that my velocity at that time is 500. Okay. And my position, I wasn't given a frame of reference, so I get to choose one. I'm going to choose my position to be 0. So I'm measuring position from where I am at the moment that this problem starts. Okay. And what I want is I want to have come to a full stop, which would mean that my velocity would be 0 at the moment in time when my position is 0.2. So I'm going to have to figure out, I'm just going to call that capital T. Capital T will be the time at which my position is 0.2, and I want to make sure that my velocity is 0 by then. Now, if I can solve for that, I'm hoping that will allow me to actually solve for d, which is what I want to know. What's the constant deceleration? So let's take a look. If acceleration is negative d, I know the velocity is just going to be an antiderivative of the acceleration with respect to time. So I'm integrating negative d with respect to time. That's just a constant. When I integrate a constant, I get that constant times my variable. I'm just thinking of that as like the slope. This would be a line of slope negative d, plus, of course, I get an arbitrary constant. Okay. So I've got that my velocity is negative d times t plus c1, but I know what my velocity is at time 0. So my velocity at time 0 is 500, but that's negative d times 0 plus c1. So that allows me to see that c1 is going to be 500. So I'm able to actually fill out my velocity function a little bit better. My velocity function will be negative d times t plus 500. Now, you'll notice my initial velocity ended up being that constant. That will often, but not always, be the case. You want to be careful. In this case, that was true because when I plugged in 0, which was my initial time, it killed off everything except that constant term. Okay. But be aware, if you don't have just powers of t, if you have a function like e to the t or cosine of t, when you plug in 0, it doesn't disappear. It becomes 1. Okay. So you've got to actually go through the work of plugging in your initial condition and solving for that constant. Don't just assume that the constant will be your initial condition. Okay, so that gives me my velocity. I don't have a full formula for it because I still don't know what this d is, but it gives me a partial formula for this, okay? And then I can go ahead and I can find my position, because I know position is going to be an antiderivative of the velocity. So it's going to be an antiderivative of negative dt plus 500, and I'm integrating that with respect to t. So that's going to be negative dt squared over 2 plus 500t plus a constant, which I'll call c2. Then I also know my initial position. I know that my position at time 0 is 0, and that's because I chose to make that my reference position. My reference position is just where I am when the problem started. So that's going to be negative d times 0 squared over 2 plus 500 times 0 plus c2. So c2 is actually just 0. It does turn out to be my initial position in this case, because I was just plugging into a polynomial, and that kills off everything but the constant term. So my position is negative dt squared over 2 plus 500t. Okay. And now what I need to do is use the fact that it's going to be the same time that makes my velocity 0 that makes my position 0.2. So if I can figure out what that time is, I could plug that in, setting position equal to 0.2, and I'd be able to solve for d. So let's see. I know my velocity at this unknown time t has to equal 0. But if I plug in capital T, I'm going to get negative d times t plus 500 has to equal 0. So that would mean that 500 is equal to d times t. So the time will be 500 divided by d. That will be the time that will make my velocity 0. But now I know at that time I need to be at position 0.2. So I know that position at this same time is equal to 0.2. So that's the position at 500 over d has to equal 0.2. Video editing has occurred. Okay, the first time I shot this video, I made a sequence of careless arithmetic mistakes that totally messed up the end of the problem. So we're doing take 2. We've gotten to this point. We've determined that the position as a function of time has this formula. Negative dt squared over 2 plus 500t, where d is what we want to solve for. D is the constant deceleration of this particular object. And we've determined that at this time, 500 over d, the position is going to be 0.2. And we're just going to use this equation to solve for d. Okay. So we're going to have negative d, plugging in for t, the 500 over d, that's 500 over d, 500 over d quantity squared all over 2, plus 500, and then again, we're plugging in for t, this quantity here, 500 over d. And that's got to equal 0.2. Okay, so this is negative d times, that's going to be 25 followed by 4 zeros, so that's 250,000 over d squared, all over 2, plus 500 times 500 is again 250,000 over d, and that's going to equal 0.2. Now here I can cancel one factor of d, so this becomes negative 250,000. And I'm just going to write that as over 2d, because dividing by 2 is the same as multiplying by 1/2, and that just puts the 2 in the denominator. Plus 250,000 over d equals 0.2. So going ahead and canceling that 2, I've got negative 125,000 over d plus 250,000 over d equals 0.2. I can combine these fractions because they have the same denominator. So that's going to be 125,000. That's 250,000 minus the other 125,000 over d equals 0.2. Let's see. Let's clear some space here. So if I multiply over by d, 125,000 is equal to 0.2d. Let's divide both sides by 0.2. So d is 125,000 divided by 0.2. I'm just going to multiply by 1 in the form of 10/10 because that's going to move that decimal. So that'll add a 0 on top. So 125 followed by 4 zeros now, all divided by 2. And that's going to be 625,000 is equal to d. And this was the constant rate at which this particle was decelerating. So that would be in kilometers per hour, which we usually write as kilometers per hour squared.